Welcome to the tutorial on Foundations for Non-Truthful Mechanism Design. This is part one on non-truthful mechanisms and their equilibrium. Before I get started, I'd like to thank Brendan Lucier and Sigal Oren for organizing the tutorials. I'd also like to thank Yiding Feng and Yingkai Li, who are going to be answering questions in the chat. Cool. So this is the Foundations of Non-Truthful Mechanism Design tutorial. Materials for this tutorial can be found at this webpage. To give some context for the tutorial, I want to begin by talking about the revelation principle. Mechanism design asks to identify mechanisms that have good equilibrium. The revelation principle says that if there exists a mechanism with good equilibrium, there exists a mechanism with good truth-telling equilibrium. The proof of the revelation principle is quite simple. The idea is as follows. We're going to take our non-truthful mechanism that has a good equilibrium, and we're going to design a new mechanism that asks for truthful reports from the agents, simulates the equilibrium strategies in the non-truthful mechanism, and then outputs the output of that simulation. It's easy to see that this mechanism has truth-telling as an equilibrium. As a consequence, much of the literature on mechanism design begins with the simplifying assumption that we might as well just look for truthful mechanisms. So there are a number of issues. First off, almost all mechanisms in practice are not truthful. And if we're looking for, theoretically elegant mechanisms, such as simple ones or ones that are robust, the revelation principle is actually not without loss for simple or robust mechanisms. And in particular, you'll notice that the revelation mechanism in the construction simulates the equilibrium strategies of the non-truthful mechanism. And these simulations can be complicated. They can depend on the prior, and that sort of breaks compromises these nice properties we'd like of these mechanisms. Finally, if we'd done truthful mechanism design using the revelation principle, but we wanted to identify a practical mechanism we could deploy, it's not trivial to undo the revelation principle and identify that non-truthful practical mechanism. So the goal of this tutorial is to present the theory for non-truthful mechanism design. Okay, part one, we're going to be talking about non-truthful mechanisms and their equilibria. I'm going to warm up with a simple discussion of the first price auction and the second price auction. Then I'm going to review general frameworks for thinking about single-dimensional mechanisms. And finally, I'm going to present the characterization of Bayes-Nash equilibrium. In this first section, we'll warm up by looking at the first price auction and second price auction through some examples. Okay, let's start with the second price auction. Many of you are probably familiar with the second price auction. The agents bid, the winner is the highest bidder, and the winner pays the second highest bid. Great. And many of you are probably also familiar with the fact that truthful bidding is a dominant strategy in the second price auction. So we're going to be analyzing auctions under distributions. And so let's do a quick review of the uniform distribution, which will be an example for our which we'll use as an example. Okay, so the uniform distribution on 0, 1 has cumulative distribution function f of z is equal to z, and density function f of z is equal to 1. A very convenient property of uniform distributions is when you draw multiple values from the uniform distribution independently, they evenly divide the interval expectation. Okay, so in particular, if I were to draw v1 and v2 uniformly from 0, 1, then the expected highest value is going to be 2/3, and the expected lower value is going to be 1/3. In other words, these two uniform random variables evenly divide the 0, 1 interval, and so one of them is at 2/3 and the other one's at 1/3. Great. This is going to make it especially easy for us to analyze the welfare and revenue of the second price auction. So again, assuming the dominant strategy equilibrium, the mechanism rules say the highest bidder wins, but under the dominant strategy equilibrium, the bids are equal to values. So the bidder with the highest bid is equal to the bidder with the highest value. Okay. Moreover, that bidder pays the second highest bid. But in this dominant strategy equilibrium, the second highest bid is equal to the second highest value. Okay, so now we're able to analyze expected welfare in equilibrium. The expected welfare is just the expected value of the winner, but the winner is the highest bidder, which is the bidder with the highest value. And so that is just the expectation of the highest value, which is 2/3. Okay, and what is the revenue? Well, the winner pays the second highest bid, and so the expected revenue is equal to the expected second highest value, which is 1/3. Great. Let's look at the first price auction. So in the first price auction, the first two steps are exactly the same. The agent's bid, we choose as the winner the highest bidder. And in the third step, instead of charging the second highest bid, we charge the winner the bid. Great. So we'd like to analyze this auction similarly, but in this auction, understanding what bidder strategies are good is more challenging. So we're first going to try to answer the question of what are good strategies, and then we'll use our answer to that to identify the welfare and revenue in equilibrium. Okay, so we'll look at the example again of two agents' uniform values in the first price auction. We're going to use the guess and verify approach here to identify equilibrium strategies, and later in this tutorial, we'll give a method for solving for these equilibrium strategies. Cool, so let's guess that agent 2 bids half of her value. And now, using this guess, let's ask what agent 1 is going to do. Okay, so agent 1's utility with value V and bid B will calculate, and that utility is given by this formula. Okay, so if the agent wins with their bid, then their utility is the value that they get for winning minus their bid, because they only pay their bid if they win. Great. Let's dive into this probability that the agent wins with bid B. Well, so this is the probability that that her bid is at least the bid of bidder 2. Okay, and remember, bidder 2 is bidding half of her value, and her value is drawn from the uniform distribution. Okay, so the probability that the bid is at least bid 2 is the probability that the bid is at least the value of bidder 2 over 2. Simplifying, that's probably at least the value is less than twice the bid. Okay, and now this is exactly equal to the cumulative distribution function. So we can plug in the cumulative distribution function for the uniform distribution, which is the identity function, and get the probability that the agent wins with bid B is exactly 2B. Good. So for two agents, uniform values in the first price auction, the probability you win with your bid B is equal to 2B. But now we have a formula for the utility of the player as a function of their value and a function of their bid, and we can optimize this formula. In particular, we can take the derivative with respect to bid, set it equal to 0, and solve. Doing so would tell us that the optimal bid given a specific value of the agent is half of the agent's value. Okay, good. So let's think about what we've done now. So we've guessed that the agent 2 is going to bid half of her value, and we've derived that agent 1 in a situation wants to bid half of his value. Okay, so in fact, bidding half of your value is an equilibrium in this auction. If both bidders think the other bidder is bidding half of their value and the values are uniform 0, 1, then both bidders are happy bidding their value, and that's an equilibrium. Great. We're now ready to calculate the welfare of the auction. And so again, we need to use the auction rules and the bid strategy to see what the welfare is. Well, if both bidders are bidding half their value, then who wins? The agent with the highest value is going to win because the bid strategies are symmetric and monotonic in value. Great. So the bidder with the highest value wins. So the expected welfare is the expected highest value, which is 2/3. Great. Let's look at revenue. Okay, so the winner is the highest bidder and the winner pays their bid. So to calculate revenue, I need to understand what is the value of the winner and how is that bidder mapping their value to bids. Okay, so all the bidders are bidding half of their value. So the revenue is equal to the expected value of the highest valued bidder divided by 2. Okay, which is 2/3 times 1/2, which is 1/3. These numbers should look familiar. So 2/3 was the welfare of the second price auction. Again, the same bidder is winning, the highest value bidder. And this revenue is the same as the second price auction revenue. This is in fact not a coincidence. And it's a general principle called revenue equivalence that we'll be discussing later in this tutorial. Great, so that was our warm-up, looking at the second price auction and the first price auction through examples. Okay, section 2 is going to be giving a general framework for thinking about single-dimensional mechanisms. You can find this material covered in chapter 2 of my textbook manuscript, Mechanism Design and Approximation. Cool. So single-dimensional linear environments. We're going to have n agents. Each agent will have a value, vi, and we'll refer to bold V as the valuation profile, v1 through vn. There will be, each agent is going to submit a bid. It will denote the bids by b1 through bn. The agents have linear utility, meaning denoting the allocation probability of the agent by xi in 0, 1, and the payment by a real number pi. The utility of an agent with value vi is vi times xi, that's their surplus from winning, minus the payment they have to make. The designer has a feasibility constraint, which will denote by calligraphic X, which is just a restriction of the set of allocation probabilities that can be produced. A mechanism will denote by the bid allocation and payment rules as follows. Okay, the ex post bid allocation rule is going to map a profile of bids, one bid for every agent, to a feasible allocation X. The ex post bid payment rule is going to map, likewise, a profile of bids into a profile of payments, one payment for each agent. Great. Given this notation, we can identify what the welfare of a mechanism is. It's just summing over all agents the value that the agent gets for receiving a service times the probability that the agent receives service given the bid profile. Similarly, the revenue is just summing over all agents the price paid by each agent given the bid profile. Looking at the single item example with the first price auction, the feasibility constraint for a single item environment is just that the profile of allocation probabilities needs to sum to at most 1, since we have only one item to sell. The first price auction is a highest bid wins auction allocation rule. Okay, so the ex post allocation rule takes the profile of bids and is going to select the allocation that's feasible and maximizes the sum of the bids. And for a single item feasibility constraint, this is just selecting as a winner the bidder who has the highest bid. Great. The first price auction is a winner pays bid mechanism. So the expected payment made by bidder I, given the profile of bids, is just the bid of the agent times the probability that the agent wins given that profile of bids. Great. There are going to be 3 stages of mechanism design that will be useful to separate. Okay, so ex ante is typically the stage in which we analyze the expected welfare or revenue of the mechanisms. This is before values are drawn, and so we're going to, in this stage, treat the values as random and take expectation over them. from understanding the incentives of the bidders, it's useful to consider things at the interim stage. So at the interim stage, this is again the perspective of a bidder at bid time. That bidder I knows their own value, but believes the other values to be drawn at random from whatever distribution they're drawn from. Okay, so this is again the interim stage of the mechanism where we're going to think about the agent strategy. And then if we want to observe what is actually happening, that's going to look happen at the ex post stage, and this is after the bids and values are known, and we'll see sort of exactly the outcome produced. Great. With this in mind, it'll be useful to compose the bid allocation and bid payment rules ex post with a strategy profile of the agents, which maps the agents' values to their bids to write ex post value allocation and payment rules in value space. Okay, so mechanism is going to be given by, again, a mapping from bids to allocations and a mapping from bids to payments. We're going to translate those mappings from bids to outcomes using the strategy profile B, which maps each agent's value to a bid, to define ex post allocation and payment rules in value space. Okay. Then to think about each agent's, the problem faced by each agent, it's useful to project these ex post allocation and payment rules into the interim stage. Okay, so when an agent's value is known, but the other agents are random. Okay, so this is what the agent is considering when they're considering how to bid. And so they face a bid allocation rule, which is we're going to take the ex post bid allocation rule and take expectations over the values of the other agents, mapping to bids using the bid strategy and plugging them into the bid allocation rule to get the probability that an agent wins and expectation over whatever else is happening in the mechanism as a function of their bid. Likewise, we'll calculate ex post, we'll calculate interim payment rules, taking expectations over everything else that's happening in the mechanism. Okay, and we can also do that for in value space. And so little xi of v is going to be just the interim allocation rule in value space, which takes the same expectation, but over the ex post allocation rule in value space. And similarly, we can have the interim payment in value space. Great. Before proceeding, I want to tell you a little bit about the notation that I'm using here. So to distinguish between ex post and interim, we're going to use the colors red and blue. Okay, and so I'll denote the ex post allocation rules in red, and these are functions from profiles of values to allocations, whereas the interim allocation rule, this is now a profile of interim allocation rules, one for every agent, mapping their own value to an allocation probability, which is taking expectations over all the other agents' values. Okay, and similarly, using the same notation for payments. Okay, so as you have seen, we'll use tildes to denote whether they're mapping from bids to allocations or payments, and no tilde means it's mapping values to allocations and payments, and red means it's an ex post allocation rule, and blue means it's an interim allocation rule. Great. So let's take this notation and apply it to the first price auction just to see it in use. Cool. So recall the equilibrium of a two-agent uniform values first price auction where each bidder is bidding half of their value, and the feasibility constraint was that the sum of the allocations probabilities has to be at most 1. Okay, so what is the bid allocation rule? Well, it just The ex post bid allocation rule, again, is just the argmax over, given the bids that we observe, of the uh, uh, maximizing the winning bids. Okay, at the interim stage, we already saw this in the previous section. The probability that a bidder wins given their bid is twice their bid. Okay, we saw this with our warm-up example. Good, mapping the ex post allocation rule into value space using our strategies, where a strategy says your bid is equal to half your value. We see that we're just optimizing this function. Okay, and in the interim stage, we see that the interim allocation rule, the probability that an agent wins as a function of their value, is just their value. Okay, there are two ways to observe this. One way is to take the bid allocation rule and map it into value space using the bid strategy. The other way is to say, oh, well, we saw that bidders are bidding monotonically and symmetrically, so the bidder with the highest value is going to win. And okay, so what's the probability that bidder I has a higher value than the other bidder? Well, when the values are uniformly distributed, the probability the other bidder is below value BI is exactly equal to VI. So this is the allocation probability of bidder I. This section is on characterizing Bayes-Nash equilibrium. You can find the original source for this material in Roger Myerson's 1981 paper, Optimal Auction Design, and you can also find it described in my textbook manuscript in chapter 2. Great. So first I want to give a formal definition of Bayes-Nash equilibrium. The strategy profile is in Bayes-Nash equilibrium if the following condition holds. For all agents I, for all values of the agent, bidding according to the strategy profile, so bidding BI of V, I, is a best response when the other agent's bids are according to the strategy profile and the values as they're drawn from the conditional distribution conditioned on bidder I's value. Okay, so in other words, bidder I thinks we learn our value VI, we do Bayesian updating on the distribution of other agents' values, and we look at the conditional distribution of bids that's induced by the strategy profile given the distribution of other agent values. And it should be that bidding according to the strategy profile is the best response for this player. Okay, just a little bit of notation. We'll denote by V minus I the vector of values with value I removed, and the conditional distribution of F given VI will denote with this notation. And of course, if the values are drawn independently, then the conditional distribution is just the product distribution without agent I. Great. So for our example of two agents, uniform values in the first price auction, as we've seen before, the strategies where all bidders bid half their value is a Bayes-Nash equilibrium. The values here we've assumed are uniform 0, 1. So the bids under this strategy profile are uniform 0, 1 half. And as we saw, the best response for any player for bidding when the other player is bidding uniform 0, 1 half is to bid half of your value. Cool. So that's what Bayes-Nash equilibrium is. I now want to give sort of this central characterization of Bayes-Nash equilibrium. First, will state sort of an equivalent definition of equilibrium in terms of the interim allocation rules of the agents. Okay, so the profile of interim allocation and payment rules are induced by the Bayes-Nash equilibrium according to some strategy profile, some distribution of bids, and some ex post mechanism, if and only if, for all agents I, for all values that agent might have, for all other values Z the agent might pretend to have, the utility the agent gets when they follow their strategy according to the strategy profile, meaning the value times the interim allocation probability minus the interim payment, expected payment, is at least the utility they would get from pretending to have value z. Okay, so this is the utility they would get when their value is v, but they get the allocation and payment corresponding to what they would have gotten when they had value z. Okay, we're also going to require another condition, which is that bids not in the range of the strategy profile are weakly dominated. In other words, this inequality says a bidder doesn't prefer to bid according to another value in the strategy profile. And this last condition says that strategies that no one wants to bid according to the strategy profile are dominated by strategies bid in the strategy profile. Great. So this first proposition just reinterprets what Bayes-Nash equilibrium means. This next theorem is going to give you a structural characterization of the kinds of interim allocation and payment rules that can arise in Bayes-Nash equilibrium. Okay, so the interim allocation and payment profile, X and P, are induced by the Bayes-Nash equilibrium for some bid strategy function, for some distribution over values, and some ex post allocation and payment rule, if and only if the interim allocation rule of every agent is monotonically non-decreasing. Okay, that means that when an agent has a relatively higher value, they're not less likely to get allocated in equilibrium. Second condition is what's called the payment identity, which is that the expected payment of an agent satisfies this formula as a function of the interim allocation rule. Okay, one quick caveat. In this formula, there is an additive offset payment of agent with value 0. In most mechanisms we'll talk about, this is going to be this is going to be 0. Okay, good. So let's unpack what this formula means, and I'm going to unpack it in showing you sort of the geometry of what the payment identity is meaning. Okay, so let's look at the first term. This is the essentially the surplus generated by the mechanism. This is the value the agent gets times the probability the agent wins. So we can depict that geometrically on this figure. Okay, so here I plotted the allocation rule as this increasing function in black. And here we plotted a rectangle with width equal to the value and height equal to the allocation probability. And the area of that rectangle is exactly equal to the surplus generated by the mechanism. Okay, the payment identity says that the payment is going to be equal to the surplus minus the integral underneath the curve. So geometrically, that integral underneath the curve is shown here. And so the payment is surplus minus this area underneath the curve. So the payment is here, the area above the curve. Great. Now, I want to give an interpretation for this area underneath the curve. And so notice that the mechanism generates this surplus by allocating to this agent with the probability given by the allocation rule. That surplus is shared. The agent gets some utility from being allocated, and the mechanism keeps some of the surplus as payments. Okay, so in other words, this surplus is going to be divided up between the part the agent keeps and the part the mechanism keeps. So the mechanism keeps the payment, and the remaining part the agent keeps, which is the agent's utility. Okay, so we can interpret the area underneath the curve as the agent's utility. Good. So this gives a simple geometric interpretation for payments, surplus, and utility, which are three quantities of interest in understanding outcomes in equilibrium. And the theorem gives a characterization that says that if if this allocation profile can be achieved in equilibrium, it has to be that these payments satisfy this payment identity. It has to be that the allocation rule is monotone, as I've drawn it here. Cool. An immediate corollary of this theorem is what's called revenue equivalence. That is, two auctions with the same Bayes-Nash equilibrium allocation have the same Bayes-Nash equilibrium revenue. Why is that? Well, the revenue comes from the payments, and the payments are given explicitly just from the allocation rule. Okay, so once I tell you the allocation rule, I'm done, and I've told you what the payments are. And so if two auctions have the same allocation rule, then they have the same Bayes-Nash equilibrium allocation, so then they have the same revenue. Notice, revenue equivalence is just sort of restating this idea of the payment identity. Okay, so often when I say revenue equivalence, I'll actually mean just the payment identity. And I want to say that while we've written revenue equivalence and the payment identity in terms of payments, I could have equally well stated this in terms of utility equivalence, because just as the surplus is just as the allocation rule guarantees the payments are given by this integral above the curve, analogously, the utility is always given by this area below the curve. Okay, so we also have utility equivalence. Great. So that is our characterization of Bayes-Nash equilibrium.